So we can't get through the membrane, but we know that ions do get through the membrane. And how do they do that? They do that through ion channels. So here is a generic picture of an ion channel. So what is the definition of an ion channel? Definition of an ion channel is one that can form a pore. The ion channel has two states. It has a closed and an open state. And the open and binding of a neurotransmitter or voltage will gate it to open. It is never gated to closed. So it's going to be in a closed situation, and a given voltage or a given neurotransmitter is going to bind here and actually open it. And that forms a pore through which ions can pass. They can pass in different ways, in different ion channels. There's a lot to these ion channels, which we'll talk about in a second. But the important thing here is that gating of these ion channels opens a pore that is open, patent, from the outside of the cell to the inside of the cell, from the inside of the cell to the outside of the cell. There is a pore that is continuous, that is connecting the inside and outside of the cell. Okay. And that is in stark contrast to a whole set of transporters, carriers, pumps. These are various types of proteins that span the membrane. They're transmembrane proteins. But what they do is they manage to get an ion from one side to the other, but they do it in a variety of ways that do not involve a pore that is continuous. So they may shuttle it. So in this instance, it's shuttled in, and then this closes off and this opens. So at no point is there a pore that goes through. The pore is either partially open this way or partially open this way. And there are just a lot of varieties of how this is accomplished, and that is essentially the diversity of pumps and carriers and transporters. And we're not going to worry about the definition of those various entities. And some of these are take ATP. Some of them are driven by an ion gradient. There are a variety of ways that these this large class of transporters works. Okay, there's one final way in which we can get across a membrane, and that is through a gap junction. In a gap junction, there are two cells. So here's cell 1 and here's cell 2, and each of the cells produces these hemiconnexins. So a hemichannel. This is producing a half a channel. This channel is no good without its pal's half channel. So both cell 1 and cell 2 have to produce the half channel, and then they have to line them up and get them to be continuous. And now, instead of having a pore from the inside of the cell to the outside of the cell, now we have a pore that goes from one cell all the way to the other cell. There's an actual connection between one cell and another cell. So what can go through here? Well, ions can go through there, but in addition, depending on how big this pore is, and that is different for different gap junctions, depending on how big that is, nutrients could go, ATP could go through there. A variety, nucleic acid, messenger RNAs could go through there. So things can go through here that can't go, that are not transported in other ways. Now, these gap junctions, this is a really tricky business to line up the hemi channels on two different cells so that they're perfectly aligned. Just to make this a little bit easier, this space here is 2 to 4 nanometers wide. So that's 2 to 4 nanometers. The membrane is, let's say, 7 to 9, something like that. A synaptic cleft is on the order of 20 nanometers. something like that. 15 to 20. So this is a very thin divide that the gap junctions have to go through. Okay, so that's how we're going to get ions across a membrane.